for Lab 6. My name is Rafay. Let's get right into it. So this is a magnetic molasses lab, or the Faraday law lab, and it investigates electromagnetic damping using a falling magnet inside a conductive non-magnetic aluminum tube. That's a bit of a mouthful. But basically the way it works is that when we drop a magnet through the tube, it induces eddy currents in the walls of the aluminum due to Faraday's law. This creates opposing magnetic fields due to Lenz's law, which slow down the magnet's fall compared to free fall. And so, by identifying the magnet's north pole with a compass and consistently dropping it north side down, we ensure some uniformity in our testing. The recording fall time that we get, basically our results, help quantify the effect of electromagnetic damping caused by the interaction between the magnet and the conductive tube. So these are just some of the principles that I've sort of already talked about, but this is basically what we're using in this equation: the Faraday's law, Biot-Savart law, and second and third laws, and then of course Lenz's law, etc., which I've already mentioned. So this is the actual experiment. That's our system, the aluminum tube and magnet surrounding everything else. And like I've already said, we use a compass to see which direction of the magnet is down. We drop it, magnetic doors face down, at least, and we do it 5 times. And then finally, we record the time that it took for the magnet to travel from the top of the tube to the end. So these are the two results that we got overall. This is our experimental time and our computational time. You can see they're pretty similar, which is a good thing. Uh, but let's talk about first the models and assumptions that we used, right? So our magnet was basically a model for a magnetic dipole, while the aluminum foil modeled tube that created an opposing magnetic force. We're assuming negligible air resistance, and we're also assuming that gravity and the magnetic force are the only other forces acting on the falling magnet. This is our, I guess you can say, average that we got. We did it 5 times. Here's some calculations here. You can look over these. But to get to the point, the average is 1.05 seconds for our experiment. And now this is basically the glow script model that we uh, use. It's pretty straightforward. We're calculating the magnetic force. We're using Newton's second law here to get the velocity and the position. And at the end, we're just going to get a velocity graph. Here's the model right here. We're defining our dipole, calculating the flux, etc. And this is basically the final graph that we got for our computational model. And the time in tube we got here was 1.07 seconds, which is a bit different from the experimental result, but not too different. Like there's clearly nothing like the actual concept is still upheld here. Oops. So just to answer a couple of the questions that we were given regarding the computational model, the blue here indicates clockwise current, whereas the red indicates counterclockwise current. So what happens to the dynamics of the system when you flip the magnet around? That just flips the direction of the magnetic field, and so the direction of the induced current reverses. But the important thing here is that the overall braking effect still remains the same because we're still obeying Lenz's law, right? So the magnitude of deceleration and terminal velocity are nearly identical, but the current directions are reversed. That's all that happens. Um, and if we sort of analyze our graph here further, at the start, gravity tends to dominate. You can see here gravity is dominating, but then as the magnet falls, the eddy currents are induced, which generates a growing opposing force. And eventually, this opposing force sort of matches the gravitational force. And what this does is that this leads to a constant velocity at the end here, uh, which is sort of a very classic sign of a system that's under velocity dependent damping, which is what's happening here in this system. So that's our computational results, right? So let's sort of talk about let's talk about why there might have been some differences. Of course, there's the obvious ones. We're assuming no air resistance, so there could have been air resistance. There could also have been sort of human error in terms of like our measurements physically, especially because it's such a small period of time. And we did do it 5 times, but there's still room for error there. And also just sort of human error in terms of we're not dropping the magnet from the same exact height, the same exact angle, and with such small numbers, that can make a big difference. And lastly, there might have been friction slowing the magnet down. Lastly, the what if and why questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? Well, in this case of a superconductor specifically, the magnet would have an almost equal and opposite force that would oppose gravity by induction. And so our magnet would be really, really slow if this were to happen. And if we cut holes or slots into the tube, all this would do is that the currents would have what looks like turbulence, basically. And so the effects of magnetic braking would be reduced. And so there wouldn't really be ring currents anymore because of the turbulence. That's about it. I hope this was a good overview of the experiment that we did and our computational model. Thank you very much for watching.